speaker today is Chris Tralie, and he will tell us, so the title of his talk is TDALabs, some of TDA's greatest hits in interactive Python. And surely everybody who, is teaching applied topology wants to use some examples. We would be very excited to hear about it.
Thank you so much for the invitation and for the introduction. This is a very unique opportunity. First of a kind venue for me, and also first of a kind sort of talk. So I'm going to try something a little risky, and we'll see how it goes. So this is going to be an experiment in running some teaching materials that I've sort of gathered over the past couple of years that I use when I'm teaching either guest lectures on topology or little workshops on topology for people who are newcomers to the field. And so I'm going to go through a whirlwind pace, a whole bunch of examples that are near and dear to my heart. So let's see how it goes. So I'm going to start off with the very basics, just to make sure that everything works. So these labs are built around a wrapper for Ripser, for one thing, which Uli Bauer made. But I worked with Nathaniel Saul at Washington State to make a wrapper for Python that actually works by compiling C on the back end. So we've got that. A couple other libraries that I've written. One of them is for alpha filtrations. I have the wrong, I was like, what's going on here? I have the wrong one open. I want to start with basic shapes. We're not ready for 3D shapes yet. Okay. So I have my Ripser. I also have a library that I've called Checkmate. Okay, so we are working on a library that does alpha filtrations and check filtrations. And then there's this persim library, which is a fruit, but also short for persistence images. And there's a whole collection of diagram vectorization stuff, but we're going to start off just using it for plotting. And then we got the standard matplotlib stuff. And I'm not going to dwell on all the code, but I just wanted to give you an idea of the libraries that were involved in Python here. So I got a Jupyter notebook fired up. I'm going to start to run stuff. So if we're honest to goodness TDA people, we should make sure that we can deal with the circle. So let's start with the circle. So I'm going to sample some points on a circle just by linearly spacing samples between 0 and 2 pi in angle. There's my point cloud, and if I run persistence, I see a nice little dot there. Okay, nice. And H1, so that's great. That seems to work. Of course, if I choose fewer samples on the circle, if I only choose 10 samples, then the birth time goes up because it takes longer for that cycle to form in the first place. All right, so far so good. I'm not seeing any complaints here. So hopefully everybody can see these notebooks. Okay. All right, so I'll keep going. So here's where things maybe start to get a little more interesting, and here's where the speed of Ripser really gets to be showcased. So what if I want to sample points uniformly on a sphere instead? Circle. So that's a little tough because the icosahedron is the best I can get, 20 points that are perfectly uniformly sampled. But one little dirty trick I can do is I can actually sample points from an isotropic Gaussian in 3D and then just normalize the lengths. And that will give me a statistically evenly sampled set of points. So I can do that, and that's what I'm doing here. And then what I'll do is, instead of using the Euclidean distance, I'll actually also use the arc length instead. So what I'm going to do is take the dot product of every point with every other point, and then take the arc cosine, and that will give me an arc length. I have to be a little bit careful because numerically the dot product can sometimes be less than -1 or greater than 1. So I have to clamp it to that range. But if I do that, and I'm in the domain of the arc cosine, then I get a nice metric on the sphere samples that I've taken. And now I see a nice point in H2. Well, and that's exciting because I just fed Ripser a distance matrix and it went ahead and figured out H2. So that's nice. It's actually fast enough to do that on this number of points. Now, one thing that I think is even cooler than that is if I just tweak the metric slightly. So if I say, instead of taking the inverse cosine of the dot product, let me take the inverse cosine of the absolute value of the dot product. Well, that's what you get when you map the sphere down to the projective plane. So I'm doing an identification there. I'm saying once you go more than 90 degrees, start to come back the other way. And it's just a simple little extra function I have to call. And what I see then is if I do this and I run Ripser, and I change the field of coefficients, I see actually I get a different answer using z mod 2 and z mod 3. And this is exactly what you would expect from the projective plane. Okay, I'm showing this now because this will come up in a real application later. But just to show you how easy it is to start getting like pretty complicated stuff in here. Okay. Now I'll skip these examples for now. These are great exercises for students to do to think about how would you sample a flat torus and make the proper identifications. But one thing I do want to show is the Mobius strip. So if I make a loop that goes around the torus, the big part of a torus in R3 twice for every one time it goes around the little part, it's the boundary of a Mobius strip. And if I look at the persistence diagram in Z mod 2, I get this, but I get a different answer in Z mod 3. So what happens actually is when I fill in the strip in Z mod 2, that looks like the death of a class and the birth of a new one at exactly that time. But we know that actually it doesn't bound at that point. So in Z mod 3, we see the true homology there. Okay. That will also come up in an application. Now, last thing I wanted to show off real quick is, and just also as a public service announcement, if you're using data that's fairly low dimensional, I said high dimensional, but this is only in 5 dimensions, I'm going to play that same dirty trick and sample 400 points on S4. So 400 points from an isotropic Gaussian in 5 dimensions and normalize that. That's still fairly low Euclidean dimension. I should use an alpha complex instead of RIPS. It'll be much faster, have many fewer simplices. So if I do that, I've done this ahead of time. It takes, okay, on 400 points in 5 dimensions, I can compute up to H4 in about a minute on my computer. And so here you see, hey, that's a high dimensional sphere. So public service announcement, if you have points that are in dimension 5 or lower, you should probably use alpha. Okay. So that's it for our basic shapes. So let's move on to now the stability theorem. So I have a little notebook called Vajratine and bottleneck. And so I have a couple of slow Vajratine and bottleneck functions, and it's on my to-do list to improve them and to actually implement the approximate thing in pure Python. If any of you would like to help with that, who maybe have more time than me, that would be great. We could collaborate. But for now, I've got a slow library, so I'm a little constrained with what I can show you. But what I'll do is I'll sample 300 points on a circle. I'll add a little bit of noise, so I'm showing you the original points in orange here, and then I'm showing you these blue points that are a little bit perturbed. And I'm going to compute the bottleneck distance and the Vajratine distance. I'm going to actually show you the matchings that I get. So in bottleneck, I'm only matching one point because it's a bottleneck. In Vajratine, I have to match every point. But in here, there's not too much noise. They look pretty similar. If I start to add a lot of noise, so if I go up to the standard deviation 0.4, then it's going to start to look a little crazy. So, and actually what I see, okay, so unfortunately I switched the colors here by accident, but the blue dot is for the nice clear circle, and the red dots are the persistence diagram for the perturbed one. And what I can see is actually it's killed it so much that in bottleneck I end up just matching to the diagonal. Vajratine does something a little bit different. It actually is a little bit cheaper to match a point. And this is the difference between the L infinity and the L2 distance, and also the fact that we have to match all of these as well. You see all those points. Can people see my mouse, by the way?
Yes, we can see your mouse.
Okay, good. So that's that. And we're also starting to get a hint that maybe Vajratine distance, well, this is really extreme. Let me dial it back just a bit. So we're starting to get a hint that maybe the Vajratine distance isn't the best thing to do because it's starting to grow faster than the bottleneck distance for adding the same amount of noise. And to really drive this point home, I'm actually going to look at a sublevelset filtration on a time series. So if I take a noisy time series, we'll look at this more in a moment, but the sublevelset filtration, I get this persistence diagram in blue, and in orange is the noisy version. If I do the bottleneck distance, I get a reasonable distance, like 0.514. That's about how much this thing is perturbed in the y direction by the noise. But the Vajratine absolutely explodes because it has to match every single little noisy peak on this curve to something, to the diagonal in this case. So this is where you really see why we need the bottleneck distance in the Hausdorff version of stability. And so I always thought this was fun to play with here, to see how much you could blow up the Vajratine and keep the bottleneck reasonable. All right, so that's like a little stability theorem thing you can do. Let me move on now to some stuff. I'm going to spend a disproportionate amount of time on this application because this is from my research. but I still have other examples on deck, so just bear with me for a moment. So one thing I work a lot on in research, actually, that I end up running workshops on and sometimes giving guest lectures on is sliding window embeddings. And to me, this is one of the most exciting applications of TDA that shows it off in places where an engineer would say, hey, I can do Fourier or something else. Well, there are actually some applications where TDA is better. Okay, so what's the deal? What's this whole sliding window thing? So a sliding window turns a time series into a point cloud. So here's an animation down here of what a sliding window does. So I've got a time series. This one's pretty simple. It's just a pure sinusoid. And I have these windows. And in each window, I take a bunch of samples of the time series. Each sample is a dimension in Euclidean space. And I slide the window along. And as I slide the window, I actually parameterize a space curve. In practice, I don't have an infinite number of samples, so I'm going to sample this curve, and I'm going to get a point cloud. And so, as part of the lab, I define what that is up here. Tau is the length between samples that I take in the window. dt is the length between windows, between the beginning of the window. And dim, that's the dimension. That's how many lags you're going to take in this window. Okay, so we can now play with these parameters. And actually, the crazy thing is, you start to get really interesting geometry if you just, this is actually still a fairly simple time series, as we'll see. Actually, on the right, what I'm displaying is not the true geometry. What I'm displaying is PCA, just for visualization. I projected these down to 2 dimensions just so we can kind of get an idea of what the geometry is. But, we can use TDA to tell us what the geometry actually is in the space that it actually lives in. So that's what we're going to do. So here's the code to do the sliding window. Here it is. It's actually not terrible. So sliding window for a one-dimensional time series is not bad at all. The only trick is you have to do some spline interpolation because I might ask for samples that were never given in the original time series. They may actually be between samples that I was given. Okay, but that's pretty standard. So here's where interactive Python gets really exciting. Great, widgets is not defined. I had to run this line first. So that's a little gotcha with interactive Python. Okay, now we should be good. So, all right. So now what I'm showing here is a time series, and I'm showing in red the window. So the window is going to be the lag tau times the dimension. That's going to be the length of the window. So if I increase tau, I make the window longer. Oh, hang on a second. This is. Sorry, let me just real quick fix this last night. Now it's acting up again. So let me just see if I can get it back to where it was. Okay, sliding window code. Now we're ready to go. So if I move this tau over, that's too bad. It's just the way it is on Windows. I increase the length of the window because I've kept the dimension fixed. So first the window was only half the period. Now the window is the full period. If I make the tau too small, I actually start getting something that's a little more elliptical. So it's important to match the tau to the length of the period, or the tau times the dimension to the length of the period. That's message number 1. If I go over the length of the period, I'm okay. This is such a bummer. The way that it worked, okay, I've had some computer issues. I'm under a different operating system now. The way this works under Linux, it actually clears the screen and it's like interactive and it updates. Now it's actually giving me a new plot each time. Okay, so problem number 1. That's okay. Just bear with me. And this is also, a meta note on software. It's always updating, always changing, and across platform. That's the nightmare of working on software. There's a lot of beautiful things about working on software. This is not one of them. Okay. But the point I was trying to make is what we're trying to do is match the window length to the length of the period. And then we end up getting the roundest embedding. That's something that Jose Pereas showed. And that's good for us because the rounder it is, the higher the persistence will be. All else things. Okay. But the crazy thing is if you just add a single harmonic. All right. If you just add a single harmonic, geometry gets much crazier. So let me just comment these out because it's unhappy with me here. Okay. So the geometry gets a lot crazier. And actually, so this is like cosine of t plus cosine of 3t. If I change it to cosine of t plus cosine of pi t, then I get a lot of errors. Now, what I actually get is a torus instead. That's crazy. Okay? So let's explore that a little bit more with persistent homology. Oh, and just one comment though. Okay, so changing from cosine of t plus cosine of 3t to cosine of t plus cosine of pi t, we see a stark geometric and topological difference, even just from projecting it down here. But if I try to use this power spectrum, which is what any engineer would tell me to do, I have no idea which one is which. It's not clear at all. 3.141, whatever, is very close to 3. Okay? But this makes a very big difference in the sliding window. All right, so let's move on to persistent homology, and let's actually measure these sliding window embeddings with persistence diagrams. So now what I'm seeing is, okay, I start with this, I get this in the projection, and here's my persistence diagram. If I do what I did and decrease tau a little bit too much, so my window is really thin, oh, this one's working. So see how this all updated in the persistence diagram? I went from a persistence of around 4 or 5 down to a persistence of 0.5. So this is not a good window length. If I make my tau big again, and I go back up to 2, then my persistence jumps back up to around 5 again. That's nice to get a nice round loop. Okay, so I can play around with tau here. And actually, once I've gone past the period, it doesn't really matter so much. I just have to make sure I get to at least the period. Ah, beautiful. I'm so glad these are working. Okay. Yeah, so now the persistence takes a dive. Okay. All right. So we've got to make sure the window length is right. Now let's go back to that example with 2 sinusoids. Okay, so again, this is cosine of t plus cosine of 3t. If I look at the persistence of that, I get some errors again. But what you would normally see is that even though when I do the projection, it looks like it has all these self-intersections, that it actually only has 1 dot in persistence. Oh, you know what? All I have to do is comment this out. I think it'll be good. See, look at that. See, my students call me the Robin Hood of code. Okay. Because I could just go in there, just comment it out. We're good to go. So, yeah, so anyway, the point is, even though when I project this down, it kind of looks like it might have a couple loops going on, that's misleading. So be very careful with dimension reduction, because truly there is only 1 loop in this embedding. It's just that the geometry got more complicated because there's 2 sinusoids there. Okay, so I only see 1 dot. Now the really exciting thing is if I change it from cosine of t plus 3t to cosine of t plus pi t, then suddenly I actually get 2 dots in the persistence diagram. Because now I actually am making a torus. Okay. So you can kind of see it in the embedding, but you can definitely see it here. And if I waited a little bit longer, you would see a dot in H2 as well, but I don't want to wait for that. Okay. That's fun. And the last thing I wanted to show, this is very surprising. This is kind of buried in Jose and John Harrow's sliding window paper. But if you make these 2 sinusoidal functions, so one is 0.6 cosine of t plus 0.8 cosine of t drawn in blue. The other one I just make 0.8 cosine of t plus 0.6 cosine of 2t. So I switch the amplitudes in front of both of these. You would expect that the sliding window embeddings of these 2 would have very similar geometry. I mean, they don't even look that different, and they both have a t and a 2t. So what's the deal? But if I go through and do the sliding window embedding on these matching the period, what I see actually is, yeah, so I keep trying to, I guess this was a Linux thing. It doesn't like this command here, trying to equalize things. Inspect, where else did I do that? Here. Okay. All right, so here's the first signal on the top and the second one on the bottom. So if I scroll over, let me make this figure a bit smaller so we can see it. I'll make this 6 by, okay, good enough. So even just looking at dimension reduction, I can see that something's a little weird about this one, where the second harmonic is stronger than the base frequency. So here, 2T has a bigger amplitude than T. And if I look at the persistence diagrams, I see something particularly strange. I see actually that if I switch, let me make this a bit smaller again, so I do 6 by 4. If I switch the field of coefficients, so I do Z mod 2, yeah, I did type layout there. If I go from Z mod 2, I get that whole Mobius strip thing going on. So actually, in the case where 2T has a bigger amplitude than T, it turns out to bound the Mobius strip, which is very interesting. So I'm using this now in analysis of rhythmic hierarchies. So if you have music that goes like 1 and 2 and 3 and 4 and that's a 2-on-1 pattern. And I've seen in data that this Mobius strip thing pops up. That's pretty trippy.
That's cool.
Yeah. And there it is. Okay, you can run it for your students. And it really took like a second. Okay. So I try to keep these notebooks taking only a second. But thank you. Yeah. So, all right. So I promised a bit of audio. So let's just do a little bit of audio. I'm not going to dwell on it too much.
Chris, can I interrupt really briefly?
Yes, please.
I had sort of a private message asking about the references. So is it correct to say one of the first references is Jose Pereas and John Hare?
That's right.
Sliding
and I probably even have
persistence?
It. Yep. Let's see. I probably even have it right in here. So look.
And then there have been some nice survey articles recently on this topic.
Yes. Now let's see. So this is an applications paper. The one I'm talking about that has all the theory. Let's go to Jose's scholar here. This is a good question. Let's take a moment. So, oh yeah, that's it. So this paper is the one where it's buried all these fun facts about like the Mobius strip, about the window length, all sorts of fun stuff. So that's the reference. Thanks for interrupting me.
Perfect. Thanks.
Yep. Okay. So now let me do just a little bit of audio. The audio is an interesting one-dimensional time series. It has a very high sample rate. So we take in 44,100 samples per second. That's so that we can capture all the frequencies we want. One thing that I was showing in one of these labs is if you take audio of a horse whinny, I'm not going to play it right now, but it actually starts off periodic and ends up quasi-periodic. So actually what it means is it ends up like a torus in some points. So I see these 2 dots in H1 here. So a horse whinny is a torus at some points. That's interesting. But if we start trying to do, so this is just looking at not very many samples. This is looking at probably this whole little snippet here is about, yeah, what is that? Like 10 milliseconds. So not very long. If I want to start to look at stuff like music, where rhythms happen on the scale of a half a second per beat, right? So Journey, actually, this Don't Stop Believin' song, which many of you have probably heard, I picked it for a reason, because it actually is 120 beats per minute, which means that every beat takes place in a half a second. Now we're starting to run into some issues with the sample rate, because we're going to need 20,000 samples to be in our window. And it's just a god-awful mess, okay? So audio is a mess. This is why I tell people who work on image processing, okay? Images are clean compared to audio. Here's audio. So if I try to do a sliding window on that, I don't get really anything. So if you ever try to do that, it's going to look like just a mess. You're not going to see anything. So there's PCA, and here's the persistence diagram. Nothing, really. And I'm expecting to see cycles because it's rhythmic. It repeats itself, and I'm not. I'm just seeing noise in H1. But there's a nice little pre-processing thing you do. If we turn to our community and audio processing, we learn that, okay, if we look at the short-time Fourier transform of the audio, so it's just the Fourier transform taken in windows. Basically, the sliding window plus an extra step with the Fourier transform. What we see is when rhythmic events occur, we get these vertical lines in Fourier. So rhythmic events are broadband. So what it means is we can kind of just look for these vertical lines in the spectrogram and create a new signal, which I computed here, which indicates rhythmic events. And actually, this is downsampled by a factor of 512, so a lot fewer samples, and it's picking up on what we want to pick up on. So when we run this, we actually get, we can kind of see the loop. It's still a little noisy, but if I scroll over, you can see in the persistence diagram now there's at least a dot that kind of rises above the rest. Okay, so this is called an audio novelty function. So I have to do, in a lot of applications, so another message of these labs is in a lot of applications we have to do some pre-processing before we can run TDA. TDA is a great tool, but trying to apply it to raw data sometimes will lead you into madness. Okay, and then I was showing that on speech, which is not really periodic, just a whole bunch of people talking to each other on a radio show. You don't see, so this is just a toy application of this, but you don't really see that dot rising above the rest the same way. This is really just noise. All right, so that was a little bit of audio. I do a lot more audio work, but the intersection with TDA is a little bit smaller. But then in my research, I also did a generalization to video. So what if I had this periodic video? So actually, you can play videos inside interactive Python. That's pretty cool, first of all. But then, so the generalization of this to video is, okay, my sliding window for a one-dimensional time series, we've taken a stack of a whole bunch of samples. Now I'm just going to take a stack of a whole bunch of frames, video frames. Every pixel in every frame is a dimension. So I've got a lot of dimensions, a very high dimensional Euclidean vector. And so just to give you an idea, as I slide this along, so this is not code I'm running now, this is just a video I made beforehand. Each one of these is a window. So it has a collection of frames, and as I slide it along, it gives me a point in a high-dimensional Euclidean space. I'm doing PCA down here to 3D, and I see it actually makes a loop, which is cool. It should make a loop if we've done this right, because it's periodic. But there's a problem. Yes?
Could you make the browser window full screen?
Sure. Is that better?
Thank you. Yep, thanks.
Yep. Okay, I wasn't sure how it was resizing it on your end. But that's okay for people? Okay.
Yeah, yes. This looks great.
Okay. So yeah, just play this one more time. So we get a nice loop for this video. Okay. If you try to do this naively, though, and you try to stack up all the frames, which I actually did at first, stack up all the frames, every single pixel in every frame, into a big old vector, you're going to run out of memory real quick. So you have to get a little more clever and actually show in code here how to do this. Actually, this is all it is. You just have to do a singular value decomposition, and you can reduce the dimension by quite a lot. So it's like saying, basically the idea is if I have 300 points in a million dimensions, I can certainly find a 299 dimensional subspace that preserves the geometry perfectly, right? That's an isometry. So that's what I do to these frames. I've got like only 250 windows in like 100,000 dimensional space or even more, actually probably beyond millions. So you do a singular value decomposition, and it makes this much better with memory. And then here's the sliding window code for a video, and I also have some interpolation here. Again, not terrible. It's all here. So now let me load in a video. So I can actually, there's some Python code I wrote that goes with these labs that allows you to load video. And if I go ahead and compute the persistence diagram, hey, I got a nice dot. Okay, so I see that the jumping jacks are periodic, at least as measured by H1. That's exciting. So then the next thing I've got to do is ramp it up to a real application, because nobody really cares about jumping jacks, right? So let me explain an application I did with Jose Pereas, which was looking at vocal folds. So this is a bit gross, but it's very cool. So just bear with me for a second, okay? So if you stick a camera down somebody's throat, a high-speed camera, and you take a video of them going ah or something, then you can use the video to see if there are any issues with their vocal folds. So, for example, okay, so most healthy people would look something like this. As I go ah, there's a periodic thing that's happening. Nice and healthy. What that means is if I do my sliding window embedding and run persistence on this, which will take a second, I will get this nice diagram. Okay, so I'm nice and healthy. I'm periodic. That's great. But here's an example of somebody who has partial paralysis. You can kind of see it in the upper left. It's not really moving as much as it should. This gives rise to something called biphonation. This is something that can happen in nonlinear dynamical systems, where you actually get a subharmonic, or you get a non-commensurate frequency introduced on top. So there's actually kind of two things going on at once. And what you see is if you compute the persistence diagrams of this, and again, the code's right here to do it, you actually get a torus. So you get 2 dots in H1 and 1 dot in H2. This is what was really exciting. This is when I knew I could graduate. When I saw this for my PhD, when I saw this image, I was like, found a torus in a video. That's exciting. Okay. And you can even see the Mobius strip in certain examples, but they're so disgusting, I think I will spare you. But if I switch between Zmod 2 and Zmod 3 in a particular example where mucus is happening, oh boy, then I'll see this whole thing where I get a different answer in Zmod 2 and Zmod 3. Okay.
Chris, we have a question that was chatted in from Umberto Lupo. So are you using the FFT preprocessing technique again here to choose the correct parameters? Yeah,
that's a good question. So I used the FFT preprocessing was used in the audio to do a downsampling and also to hone in on the kind of features I want. Here, I actually don't do any preprocessing on the video, and that's one thing that's exciting about this. I don't have to use any fancy computer vision techniques to track anything. As long as these videos are relatively stable, and I've quantified that in another paper, based on, like, if your camera's not jerking around too much, then this will actually pick up on the loops, which is cool. But there actually is another preprocessing step I do. I mean, not in these labs, but in the paper. In these labs, I kind of tell you exactly what the window length should be. But you don't really know what the window length should be in practice. So there's a step that I like to do, which is actually not based on Fourier, but it's based on autocorrelation. So there's a lot of work in the audio community on something that they call pitch detection, which is you want to figure out what's the fundamental frequency. It's like if you're trying to follow somebody who's singing. So I turn to that literature to find a technique to just run on the video at the beginning before I do anything, just to see what the fundamental frequency is. But that's not, so it turns out Fourier and autocorrelation, as I've empirically shown, are also not the best for measuring degrees of periodicity. So I can use them to kind of tune my window length, but then this TDA tells me a lot more. So I think this is an honest to goodness application of TDA that leverages the pre-processing that we want from engineering, but then says something a little new. And I still on my to-do list. Oh yeah.
Sorry, to carry on. And have you considered using some of the techniques that are often cited in the literature that are based on mutual correlation, mutual information, and false nearest neighbors and that kind of kind of mumbo jumbo? Have you tried those, and do they work less well here?
I haven't done like extensive experiments with that, but I think because we're dealing with periodic signals here, we can just rely on the fact that we're looking for something that's periodic, so we'll do an autocorrelation, and then we'll do that. And then as long as you choose the appropriate dimension, it's okay. I don't worry too much about false nearest neighbors. I just choose a dimension that I know is going to work.
Mm-hmm.
And
Thank you.
It's fine. Yeah, does that make sense?
Yeah, thank you very much.
But those are good little hacks there. I love those tricks. False nearest neighbors, that's a good one. Okay. I mean hack in the best possible way. All right. Okay, so let me move on to some other applications so this is not so chauvinist about sliding windows. Because there are a lot of other cool things that people have done in the community. So let me show you now, let me move to image patches. Okay. So I'm going to import a bunch of stuff that's going to help me deal with image patches. Okay, so what do I mean about image patches? So let me start with an image first. So here's an image of a disk. It's a 50 by 50 image. And if I'm inside the disk, it's white. And if I'm outside the disk, it's black. Now, anybody in graphics or image processing would be cringing at this image because it's horribly aliased. Okay, it's got these jaggies here. Whatever. This is fine for our example. So now what I'm going to do is I'm going to take all 5 by 5 patches in this image. Okay, so if I do that, I get all of these patches. So every single 5 by 5 patch I'm going to sample from that image. And now I want to know, well, do these patches concentrate on something interesting topologically? So each patch I can think of, since it's 5 by 5, as a point in a 25-dimensional Euclidean space. So each pixel is a dimension. Here they're a little bit boring because the pixel's either going to be white or black, so like 1 or 0. But in general, they can be grayscale, so anything between 0 and 1. And what I see, actually, if I run this through Ripser, what I get is some H2 going on. Okay, so let me say that again. What did we just demonstrate? We just demonstrated if I take this image of a disk, I take a whole bunch of little patches that witness it, and then I take persistent homology, I see H2. So somehow these patches collect themselves on a sphere. The reason is actually because, okay, so the North Pole is basically the patch that's all white. The South Pole is the patch that's all black. Patches that kind of are half black and half white are along the equator. Patches that are more white than black are more towards the North Pole. And patches that are more black than white are more towards the South Pole. And you can actually see it here. It's that simple. It's really not much code to demonstrate that. Okay, so that's the first kind of warm-up example. But one that's actually applicable is particularly for line drawings, so like of digits and things like that. If you take all patches that witness line segments at different orientations and different lengths from the center of the patch, then here's that whole collection. And the question is, well, does this concentrate on an interesting topological manifold? And I wouldn't be saying it if it didn't. So have we seen these diagrams before? So again, you just run this code and you get it. So all possible line segments that go through a square patch. Turns out we get that's on the projective plane. Okay. So with Z mod 2 we get this diagram, and with Z mod 3 we get this diagram, and that's exactly what would happen for the projective plane. And if you're not convinced, you can even go a step further. So Jose Pereas has, you can tell I work with Jose. So he's come up with this technique for Eilenberg-MacLane dimension reduction. And you can actually find, if you think it's on the projective plane, you can find a map from the points to the projective plane. And we're currently working on a library to do this actually in Python. And I have a student even help me out on it. It's going to actually be between Python and JavaScript, so you'll be able to see some demos of these Eilenberg-MacLane coordinates in the browser. But here's what you get. So here's when I map these patches to the projective plane. Let me just zoom out a bit here. Okay. So, and the code is here running, although this code is a little hacky because the library is not done yet. But what you see is actually the patches with the line going towards the center concentrate towards the equator of the projective plane, and the ones with the line segment towards the boundaries concentrate towards the pole. And the reason is because the line segment going through the center, as soon as I turn 180 degrees, I'm back to where I started. So that's why we get this twisted geometry in natural image patches. It's because of the 180 degree thing. Well, of course, in grad school, I was talking to one of my advisors about this, not John here, but my other advisor, Guillermo Spear. He's like, well, of course, the image processing guy is like, you turn an image around 180 degrees, it lines up with itself. Okay, so what? But the cool thing is, so Jose has actually used this to come up with a new basis for image patches that matches the geometry better. So you can do a little better than what JPEG uses, which is the discrete cosine transform, if you actually use the fact that these patches concentrate on the projective plane or some other patches that concentrate on the Klein bottle. So I always thought this was an amazing thing. This is another application that I think is just a star application of TDA. It's like we use these insights to design a new basis for image processing that does better. You can compress things better and reconstruct things better with this basis. All right, so that's image patches. All right, so just a couple more applications. We're getting towards the home stretch. So another one that's near and dear to my heart, I haven't published as much on, but I've worked a lot on. I'm getting close to having stuff that's publishable, but it's not quite there. But so we're going to actually dig into these sublevel set filtrations. So just to review, and I'm only going to look at H0 here. Okay, so I'm only going to look at connected components. So just to review that real quick. So here's a bunch of points, and here's H0. This is not the best application of H0 for Euclidean point cloud, but we say in this application that every point is born at time 0, and then it might merge later. So once I go past this dot, I see that this cluster here merges with this cluster here. Okay, so this is my threshold at which I connect things. So the persistence diagram at least tells me, well, when do the clusters merge? But this is really just the same thing as what single linkage clustering does. So let's get to something a little more exciting. So this is where we get to the lower star filtration. So now let's say that we have a time series. And what we want to look at are the sublevel sets below a particular value, below a particular height. And this is what the lower star filtration is. So if I move this up a little bit, okay, so this orange line kind of shows me my height. And I add all the vertices below there. And I add an edge if both of its vertices have been added. That's the lower star rule. And you can think of this as actually raising water over this landscape here, this porous landscape, I guess you could say. So I've got a little valley of water here, a little valley of water here, a little valley of water here. And now I've got another little thing starting on the left here. But when I get to a local max, it's going to merge. So that's actually a death event in H0 for these sublevel sets. So once I pass by the maxes, I have a death event. And see, there's another merge that just happened there. So right before, here I am, and now I'm going to merge. And then finally, I'm going to merge up here. And then there's the infinite class, right, for the whole thing. What I really like about this, okay, well, so first, here's a cute example. So here's just sine of t plus t. And you get this nice little diagram that's just a whole bunch of points on a diagonal line, which is nice. Because the mins keep increasing along the line t. That's fun. And same thing with the saddles, with the maxes here. What I really like about this, though, let me use the sign to show this. If I warp my domain, see, look, I'm warping this signal. So I'm reparameterizing my time series. The persistence diagram doesn't change at all. So these are actually, if you've done your sampling properly, these are invariant to reparameterization, these sublevel set filtrations. So it's like if this is somebody singing, it doesn't matter if they start off singing more slowly, or actually here they start off singing more quickly and then more slowly at the end. I'll get the same persistence diagram. I do run into some issues if I don't have enough samples. So I'll see, the persistence diagram does kind of wiggle around a little bit here. If I don't have enough samples, just because, you do have to sample things properly to actually hit that local min and that local max where they should be hit. But you can see they're not too different. So this is a nice descriptor for things that can be reparameterized. Okay, but the really fun part is with images. So you can do the same thing with images. You can do a sublevel set filtration on images where I add edges as soon as the pixels have been added. And I can use this actually to do something like cell segmentation. So say I take this image of wood cells, and I turn it into a grayscale image where bright is actually 0 and dark is 1. I end up getting this persistence diagram here. And what I can do is actually use that persistence diagram to design a segmentation threshold. So here's where it thinks all the cells are, but I'm just being a little bit too liberal with the threshold that I'm choosing. So if I up my threshold a little bit, I can actually really hone in on. So I'm saying I only want to keep the connected components that have a lifetime that's longer than 0.2 here. And here we get them. So you see this is actually a pretty good threshold. If I move it down a bit, you can see I get some more of the cells that I might have lost there. If I move it up too much, I lose a lot of the cells. So this is a little bit too coarse. So this is a nice way to tune it. You can just look at the persistence diagram and say, hey, you know what? It looks like most of the important stuff is up here. So let me make sure I choose my threshold that's less than that. And this down here is probably just noise. So I always love that. In the interest of time, I'll go quickly through this 3D shapes one. So I also have, the 3D shapes one. You don't have to do this lower star filtration on a regular domain, like a time series or an image. You can actually do this on a shape, like a mesh. So some people so Steve Udo and others, I can give the reference. I should have provided it here, but they've shown, okay, one thing you can do is, let's take this triangle mesh, so it has a bunch of vertices and connectivity information, and if you use as your function for the lower star filtration the height, you get different persistence diagrams based on what pose a person is in. So here they have their hand kind of up. So there's a component that's born at both of the feet, and then another component that's born at the hand. You can see it here. The 2 feet merge here, and then the hand emerges around here at the shoulder. If I go to a different pose where they've got their arms down, then I don't see that second dot in the same place. Oh, this is a little different because we have their face up there, which is the one I was looking for. 2. Okay, but the point is, you see things that are a little different. Okay, yeah, here they have both their arms down. You can see like that. So they use this to say, okay, what pose is a person in? There are definitely easier ways to do that, and that's maybe just a cute application. But the application where this gets really interesting, and you can cluster by that. Okay, so let's say I do the Vajratine distance between these persistence diagrams. I can cluster by that. But where it really gets cool is if you actually make your function for the filtration be an intrinsic function. So let's say I had this hand. So, and what I'm going to do is have a function that picks up on curvature. So I'm using this heat kernel. That's the HKS that somebody mentioned at the beginning. There's a library I've written that's a little bit rough around the edges that you have to check out separately if you want to do this example. Just follow the directions on TDALabs and you'll get it. But it's something that picks up on curvature. So you see the fingertips are much more highly curved than other areas on this thing. And so if I add the fingertips first and then they merge together where the fingers meet. Oh, by the way, I have a Mobius ring. Okay, my wedding ring. But anyway, so they merge when the fingers meet. That's a death event. And the really cool thing is if I start moving my fingers all over the place, so here they're pretty much straight up. If I move my fingers around, oh, now I'm onto a different. I moved away from fingers. Okay, let's do ants. Ants is an even better example that I like here. Okay, here's an ant. The ant has a lot of fingertips too, or whatever you would call them. So I see a dot basically for each tip of the ant. And if I start to move the ant around, I will still see a similar diagram, even though they're moving all over the place. So this is cool because I can recognize that it's an ant even if it's moving its arms around. So that was a nice thing that they showed there. Finding these isometry invariant 3D shape descriptors that are descriptive is a difficult thing. And they showed in this paper that it's actually a pretty good thing to do. All right, so the very last thing I'm going to share real quick is just something that people are getting more and more interested in machine learning on persistence diagrams. And I just did just a tiny bit of this. I presented something, or actually Francis Mata presented this on behalf of us in Boca Raton back in January, or in December. But so one of the applications we looked at was, so we're trying to do machine learning on persistence diagrams. And one of the applications we looked at was these so-called trabecular bone tissue. And this is not, by the way, this is the one thing I'm showing you that's not actually online because I'm not sure if I'm allowed to share this data yet. So this is an exclusive look at the data. Okay. So there's something called trabecular bone tissue, which is porous bone tissue. You can find it in the femur. Actually, all of birds' bones are trabecular. What it is, it's kind of this spongy tissue that's supposed to be able to stretch and compress. So it has holes in it. It turns out the bigger the holes, the better, because it can stretch and compress more. That's healthier bone. When they start to fill in like this, as I understand it, that's less healthy, and maybe that happens during osteoporosis, for example. But for us, as much as I know, is that holes are important for bones, okay, for trabecular bone tissue. And so I have got about 50,000 samples. So again, I'm going to use the alpha filtration. I'm not going to use RIPS. That's going to be way too slow. Use alpha. I'm in 3 dimensions. Okay. And I get these persistence diagrams. So here I've got smaller holes. Here I've got bigger holes. Then to learn on this, I actually make persistence images. So this is one of many ways you could vectorize a persistence diagram, but it's one that I happen to like. It's basically creating a heat map for the persistence diagram. So you can kind of see the heat map is on the right. So I'm turning the persistence diagram into an image. And also have something called the trabecular number. So for the bones that have bigger holes, this number is smaller, and the bones that have smaller holes, this number is larger. So we can actually do a regression. We can do supervised learning on this. The problem, though, is I only was given like 16 bones from the collaborator I was working with. And data is precious, and so I wasn't going to complain, but I had to figure out, okay, 16 bones, and persistence images have like 10,000 parameters. Doesn't seem like enough, you know, it seems like a bit of an under-constraint problem. So you're going to have to apply some kind of regularization. So what we did is we did ridge regression, which is a very simple linear regularized least squares thing. So in addition to trying to find the least squares solution for the regression coefficients on the persistence images, you actually also minimize the squared Euclidean norm of the coefficients. And so what we showed, this is kind of fun. So there's a bunch of hyperparameters involved in the persistence images. You have to choose the resolution of the persistence images. You have to choose like sort of the width of these Gaussians that you put over each point. But then there's also this hyperparameter for the regularization, right? How much am I regularizing? So you can do a grid search, or as we showed in the paper, you can do a Bayesian hyperparameter optimization. But regardless, you can find an optimal amount of regularization fixing the other hyperparameters. So if I say I want my persistence images to be pretty coarse, what I find is I don't need that much regularization. But if I want my persistence images to be finer, so I've got a lot more degrees of freedom, I need more regularization and ridge regression. And also, the really cool thing is I get a different regularization parameter for ridge regression, but I actually see what looks kind of like a super resolution version of the coefficients between the coarse and the fine. So using a different but minimum mean squared error regularization parameter in the ridge regression gives me just an upsampled version of the coarse. So that was very cool. So we did some experimentation in this paper to see, well, how did all these parameters play with each other? And once you dig down into it, it's actually fairly intuitive. But so that's basically all I have. I mean, I have other things I could go through, but that was a lot. So I should probably just stop and see if there are any questions.
Yes,
so,
questions.
Yeah.
Okay, so I'm not hearing anything. So what is what other do you have plans to include other things too? I mean, I know that it's still pretty much a work in progress, but what are your ambitions on what other things to include?
And let me just interrupt to say, even though it's a work in progress, it's almost all publicly available online, which is fantastic.
Yeah, so you can use it now. And in fact, I think a couple people have. But yeah, no, I definitely is still a work in progress. And part of this talk was to kind of recruit help. So anything that you think is included, I could tell you some of the ideas that I've had that I definitely want to put something in with proteins and weighted alpha complexes. I definitely want to put something in about this, what we're seeing with astrophysical data, like the galaxies and things like that. Oh, I forgot to show a little punchline. I forgot to show in the lower star filtration for images. There was this tweet that somebody said when the black hole thing came out a year ago, where they were able to image the black hole. Somebody on Twitter, this guy Mitchell Athon, was like, you know what? We work in the best field because we could tell you that there's a hole in the black hole.
Oh.
And actually, if you want to do this in your class, you could do this, and here it is. So there's that black hole image in there. We see it.
Oh wow,
okay.
That's really cool.
So that took a second. You could do that in your class, and then obviously, TDA is a great field. Okay. But yeah, so let's see. So that's an application, but but other astrophysical data that's maybe a little bit less obvious. So there are people who are working on that. Stuff with plant roots. I would like to see in there. I'm doing a lot of work on merge trees. I have a lot of code for that also that I can put in there. So there's a lot to do. And if you have any examples you would like to include, I would love to include them. So that's part of the message. Any ideas that I haven't mentioned? Since you asked that question.
Oh no, no. I'm actually. I have to say, I'm very happy that I see the sliding window nicely explained, sort of.
Oh, good. I'm glad that that's your assessment. Yeah. So all the code's there. So you see the code isn't terrible.
Exactly.
It's all contained.
Because that's something that I've been wanting to include. So this is the part that excites. I mean, I'm very excited about because I can now finally sort of show it to other people too.
Good. Excellent. And if you run into any problems, please let me know. Yes, GitHub has a nice, robust issue tracker as well, which I often take things from.
Yeah. So, well, if does anyone else has questions?
I'll ask a question, Chris.
Yes.
So there are a few other functionalities that, for instance, some of the other packages give, for instance, generators of the homology or persistent homology groups. Do you have any plans of implementing that as part of something that's available through scikit-TDA?
Boy, that would be great. So, are you one of the people who did the stuff with linear programming?
I'm Nathaniel's advisor, Bala.
Yes, you are. Okay, I thought so. Nice to meet you. I would love to get that linear programming stuff in there. I always thought that was such a cool paper. Beyond that, I'm by no means an expert on generators.
Not even the optimal, not even tightening the loops, but even just extracting generators for the homology.
Oh yeah, this is like the yeah. So just what comes back from the persistence algorithm. This is like the most requested feature that I haven't had a chance to implement. Yeah, that wouldn't be too bad, but I've got to dig into Ripser a little bit to actually get that. At some point, I just want to write my own Ripser. So yeah, I would love to have that. People keep asking for that, and it's a shame that we don't have that. So my apologies, but I agree that would be very useful.
So many of the software packages spit out some cycles. Ripser does not. Is that correct to say?
Not right now. Yeah. What we do spit out, which is interesting, because it actually works with cohomology, and this is the reason it gets a little tricky to spit out cycles.
I see.
Ripser is implemented on cohomology, so what you return is cocycles.
I see.
And that's useful for what we're doing with projective coordinates, so that's great. Mm-hmm. But we would have to actually go and implement, persistent homology, not persistent cohomology, to get the cycles.
I see, which might make it quite slower. I mean, that's one of the reasons why Ripser are so much faster than other software.
Exactly. So that's kind of what's going on. I mean, you could probably bully a cocycle into being a cycle, but I don't know. It starts to get a little weird. So that's kind of where we're at right now.
Oh, so we have one more question. What limits on point cloud size are there? Can you hear me? Or
it looks like we lost Chris momentarily. Let's see.
Well, I can still see him online, but well, I'm happy we lasted until the end of the talk.
We'll give him a second to see if he rejoins.
Okay, so Henry, what do you think? Should we wait or should we just finish the recording?
Let's, Sarah, why don't you lead us through the finish line? Let's give Chris a round of applause, even though he's not here.
Yes, So thanks everyone for joining. So we had like a and we thank Chris, although he's absent. And now he's back, I see. Well, I'm still...
Can you hear me? Oh, sorry about that. Yeah. As luck would have it, my power strip broke yesterday, so I just ran out of battery, but now I'm back.
Okay.
So, sorry about that. So point cloud sizes, for H1, it's like you can get away with around 1,000, so still not too many. H2, I would say in the hundreds. But for alpha, you could go up to tens of thousands if you're in low enough dimensions, which is nice. The other thing is, one of the really cool things about Jose Pereas' projective coordinates and circular coordinates is that you can actually, they work. The algorithm, it's both a feature and a computational part of the algorithm that you subsample the points at the beginning. So it goes much faster. And you actually want to do that because you're trying to find these partitions of unity from a cover. So you want to take a subsample. So we're excited about projective coordinates as another way of doing dimension reduction that won't be too slow, even though it does have to do persistent homology up front. So still a little slow, but getting there.
Okay, yeah. So you were absent when everybody applauded you for giving
us. Let's do it again.
Yeah, should we do it again or?
Oh, certainly. Yeah, everyone, please go ahead and unmute yourself.
Let's do it again for
Chris.
Thank you.
So thanks everyone for joining us. The next talk will be in 2 weeks. So we'll see you then. And,
thanks again.
Bye. Thank you, Chris.
Bye.